Can you 3D print a high-performance magnet that actually keeps its power? Traditional wisdom says no. Heating magnetic powder enough to shape it typically ruins its internal structure. This paper challenges that limitation with a clever two-step process. On one hand, using laser powder bed fusion, or LPBF, promises design freedom for motors and generators. On the other hand, the intense heat required to melt the metal creates magnets with very low coercivity, making them useless for high-temperature applications. To solve this, the researchers proposed decoupling the shaping process from the densification process. Instead of trying to print a solid magnet directly, they print a porous scaffold first, and then fill the gaps with a special alloy. Let's break down exactly how this two-step manufacturing method works. First, they use a laser to lightly bond spherical magnet powder. By keeping the laser energy low, they create a structure that is only 65% dense, which crucially preserves the delicate nanostructure of the original material. Next, they coat this porous part with eutectic alloys containing elements like neodymium and copper. When heated to 650 degrees Celsius, this coating melts and wicks into the magnet's pores like water into a sponge. As the liquid alloy penetrates the structure, it does two things. It fills the physical voids to increase density, and it forms a non-magnetic shell around the grains. This shell magnetically isolates the grains, preventing the reversal of magnetization. So, how effective is this infiltration technique at restoring magnetic performance? The results are substantial. While the printed part started with a coercivity of just 0.65 Tesla, infiltrating it with a terbium-rich alloy more than doubled that figure to 1.52 Tesla, actually outperforming the raw powder itself. Beyond magnetism, the process heals the material structure. The infiltration fills the voids to reach near full density of over 7.5 grams per cubic centimeter, while simultaneously eliminating soft magnetic phases that usually degrade performance. The secret to the highest performance lies in the specific alloy used. When terbium is added, it replaces neodymium at the grain surfaces, creating an exceptionally strong anisotropy barrier that locks the magnetic field in place. To learn more, head to emergentmind.com. By combining porous printing with alloy infiltration, these researchers have unlocked a path to 3D printing complex, high-strength magnets.